In this lesson on electric circuits, I'll be talking about the relationship between current, voltage, and resistance, and that is what we refer to as Ohm's law. We'll do some calculations that go along with that, and I'll also talk about series and parallel circuits and some of the calculations that go along with that as well. So this picture here, it does show us an electrical circuit, which really just means that we have some sort of a device, the source that we have here, in this case a battery, that's going to be moving electrons through a wire or a conductor. Here we also have a switch to control the movement of the electrons, the current going through the wire or conductor, and we have a load, in this case here a light bulb, that is then turned on whenever we do have a current that is going through that conductor. So just as a little bit of an analogy here, if we think about a river or a stream, so what we have flowing down the river or the stream of water, the flow, well, of course, we do refer to that in terms of the river. If I put a river over at the side here, so that, of course, is just the current. The current is the flow of the water that is going through the stream. If I jump down to the bottom here, why is that water flowing? There needs to be some sort of a push, and usually that's an elevation change, so we'll just say that there is a slope that is giving it the push to allow the current to flow. And then there are all kinds of things that are going to slow it down. So in this case here, we have the bottom of the river, we have the sides of the river, we have some vegetation that's going to slow it down. And that we'll just call, well, the resistance, because it is resisting the flow of the water going through the river. So now if we do talk about electricity, well, the flow is going to be electrons that we are dealing with here. Not water, but electrons that are going through a wire or going through a conductor. So just like with water, it's still called the current. So the flow of electrons through a conductor is called the current. What is going to slow down the movement of those electrons are interactions with the atoms that are in the conductor, and it is also just referred to as resistance. In the case of the push, though, it's not the slope, it is something different that we're talking about that is going to be moving the electrons, pushing the electrons through the conductor, and that is what we refer to as the voltage. The voltage or the potential difference. So we're going to talk about these three here, the relationship between them. I'll show you a simple little animation, and then we'll take a look at the equation, Ohm's law, and we'll do a simple calculation that goes along with that. So symbols that you do need to know about and units that go along with them. So these are the three things that I just mentioned, current. So in terms of electricity, the symbol that we use to represent current is a capital Y. The units for current are amperes or amps, and we use a capital A to represent that. And that is simply the amount of electrons measured in coulombs per second that are going through that particular conductor or wire. Voltage or potential difference, this is the push that we're talking about that's going to cause the movement of the electrons. The symbol is capital V, and the units is also a capital V, and those are the units of volts. And finally, what is slowing down the movement of the electrons going through the conductor? That is the resistance, capital R for resistance, and the symbol for this one, this is the Greek omega symbol, and that is for ohms. Those are the units for resistance. So the relationship that we do have here, this symbol here means a direct proportionality or direct relationship. As one goes up, the other one goes up. As one goes down, the other one goes down as well. So there is a direct relationship between current and voltage, a direct proportionality. What does that mean? The voltage goes up, and we're going to see the current that goes up as well in proportion to each other. So if the voltage is going to double, then the current is also going to double as well. With the resistance, now the greater the resistance, the lower the current is going to be. So instead of a direct proportionality, we have an inverse relationship here. And that's why we have that proportional sign over 1. 1 over means that we have an inverse relationship. So in this case now, as we have the resistance that goes up, what we're going to find is that in terms of the current is going to go down. There are more things that are interrupting the flow of the electrons that are going through that conductor. So taking a look at these relationships and these three different variables, what we can then say is that the current is, again, directly proportional to the voltage. So we would put that in the numerator. I'm just going to rewrite this again. So this backslash here, that does just mean divided by. So if I write it this way, voltage over resistance, or you might like it this way, voltage divided by resistance. And again, that just means that as the voltage gets bigger, the current gets bigger. But as the resistance gets bigger, the current is going to be decreasing. The form that it actually gives you and what is referred to as Ohm's law is this one here. This is in your data booklet. So voltage is now directly related to the current and the resistance, and that is Ohm's law. So I'll show you a simple little animation here, which just kind of takes us through this relationship, taking a look at current, resistance, and voltage. So it's showing a really, really big V here, a really, really big R, and a somewhat smaller I. So take a look at those symbols, and by changing the size of them, that's going to indicate, at least qualitatively, the change that we see in the voltage, the current, and the resistance. Down at the bottom here, what we do have is our circuit, this big loop that we have here. In this case, it is batteries that we're using, so this is going to be direct current. And it tells us that these three batteries that are lined up in this particular fashion, which is referred to as in series, we simply add them all up. So 1.5, 1.5, 1.5, and that's this number that we see here. The total voltage is 4.5 volts. And what we can do is we can actually change that voltage, and that's what I'll do in a minute here. So once we do have this circuit completed, then the electrons can go out of the battery, they can complete the circuit and go into the final battery here. And that means that we do have some current that is flowing, and they tell us what the current is in the middle here. So the M is for milli and the A is for amp, so this is 9 milliamps that we're talking about. Down at the bottom, the cylinder that we see here, that is some sort of a device that is interrupting the flow of the electrons. So it could be a light, for example, that is causing this resistance. And so that's our capital R in terms of the symbol. And as we see, we can change that as well. Right now, it has it at 500 ohms. So what is the relationship? Well, what happens if we, first of all, increase the voltage? So if I add more batteries in series, that's going to increase the voltage. So if I bump this up, add another battery, take a look at what's happening with the size of the symbols. The V is obviously going up, but take a look at the I as well. The I is getting bigger. We're not changing the resistance. That doesn't change at all by increasing the voltage, but it does change the current. And if I do the opposite, if I decrease the voltage, then we can see that the current goes down. So that tells us that there is a direct relationship between voltage and current. The higher the voltage, the higher the current is going to be. So what if we now change the resistance? So if we have less resistance, again, think about a river, we're going to have more current. So if I make the resistance lower, we should see this capital I getting bigger. That's not going to change the voltage, but it is going to allow more electrons to travel through the conductor. So again, as resistance goes down, current goes up. As resistance goes up, the current goes down. That has no impact on the voltage. Okay, so kind of nicely showing that relationship between these three different variables that are involved in Ohm's law. So in your data booklet, you do have all of this information in terms of the variables and the equation that we're talking about right now. So electricity formulas, if we take a look along the right-hand side here, it tells us, well, capital R is for resistance, and there are your units of ohms. I is for current, units are amps, V is for voltage, and capital V the units for that one as well. The equation that we're talking about right now is this one, so V equals IR. So remember, you do need to know how to rearrange this equation. So you might be asked to solve for the voltage, and this would then be the form that you would use, but you may need to solve for the current, or you may need to solve for the resistance. So let me just quickly show you those different manipulations. So if I now need to solve for the current, that means I need to get resistance over to the other side. So I like to write these over 1, and everything so far is in the numerator. So if I want to get current on its own, I need to move resistance over to the other side. If it's in the numerator on one side, to get it to the other side, I just put it in the denominator. So what does that mean? Current is now going to equal to V divided by the resistance. What if you need to solve for the resistance? So very similar, only now instead of moving the resistance to the other side, I'm just going to move the current to the other side. And again, that's going to end up in the denominator. So this would be the equation that we then have. So there should be voltage in here. Voltage divided by the current to give us the resistance. So those are 3 different forms of the equation, depending upon whether you need to solve for the voltage, the current, or the resistance. So let's take a look at an actual calculation here. So here we do have what is called a schematic diagram, which is showing us a circuit. So all of the lines that you see here, that is our wire or our conductor. We do have a voltmeter at the top here, which is measuring the amount of voltage that is going through this wire. So this would be a voltmeter, just telling us what the voltage actually is. And we can see here that it's 10 volts. So remember, whenever you're solving these problems, always use grasp. So what is our given information? Well, we're told that the voltage, either from the diagram or up above in the text, it tells us that it is 10 volts that we're dealing with for the voltage. We're trying to figure out the current, so that would be our required information. And we're also given the amount of resistance, both in the diagram and up above here. So capital R resistance is equal to the 500 ohms. So in this picture, what is going on is we're going to have this battery here. So this is the symbol that we use in a schematic diagram for a battery. And that's what's going to be moving the electrons through this conductor. So as soon as you flip the switch, they don't have the switch here, it's going to get the electrons going in this direction. We need to complete the circuit, so it goes all the way around to the other side. We're measuring that it's 10 volts. We know that we have a 500 ohm resistor. So now the question is, what is the amount of current? So we can measure current using another device, which is called an ammeter, that we would stick in here. And we can calculate what that would actually be. So for our analysis, we know that voltage is equal to current times resistance. Here we're solving for the resistance. So what we're going to do in this case is, of course, get the current on its own. So as we just talked about, that means the current is going to be equal to the voltage divided by the resistance. So the voltage in this case is the 10 volts. Always put the units in here, put the units in when we get to plugging it into the equation as well, divided by 500 ohms. And here we end up with an answer of 0.02. You can plug those numbers into your calculator, and it is current, so the units would be amps for this calculation. So 2 different kinds of circuits that I'll talk about here now, parallel and series circuits. So it has these series circuits on the left-hand side, so I'll start with that one. With series circuits, what we do have is, well, in the case of all of these circuits, we have wires, which are the lines, so those are the conductors. What we have is something that is driving the movement of the electrons, so this is a cell or a battery, and it does have at the bottom here that we do have something providing the voltage, but we'll just say that it is a battery because that is what we're talking about at the bottom here as well. And then what we have are different resistors. So if we do have one single big loop for the resistors, for lights, for batteries. They're lined up in a row, but in each one of these cases, what we have is one big loop. Big loop here, big loop here, and a big loop here. So if you have just one big loop, whether it's the resistors as it's shown, the electrical appliances, or the batteries, that is what we call a series circuit. And what that means is that the current that is going through here, it's going to pass through each one of these that we do have, regardless of whether it is the resistor or whether it is the lights, or what we're going to be doing with the batteries is we add up those voltages to give us the total amount of current that's going through this one big loop. So how is that different with the parallel circuits? Well, with these ones here, what we can see is that now, and this is the key, it's not one big loop, but what we have are some branches. So you can think of this as being different loops. There's a loop here, there's a loop here, there's a loop here, whether it's the first picture that's showing the resistors, or the next one with the lights, or the last one, we can also have the batteries that are in parallel here as well. So the big key is big loop, no branches. And with the parallel, we have a whole bunch of these branches. So you should definitely be able to identify different kinds of circuits, whether they are parallel or the series. And these are just the schematic diagrams. So this here, this would be our battery. This is our battery in both cases. So in these situations, we have one single battery that is providing the driving force for the electrons or providing the current. For the parallel circuit, the electrons can either take this branch, or this branch, or this branch. Because they can take three different branches, what we say is that the current that's coming out of the battery in the first place, it is divided between these three different branches that we have. In the case of the series, again, what we have is a big loop here. So now we have the same current that's going through each one of these. So those are the schematic diagrams. Again, this is the symbol that we use for the battery. This is the symbol that we use for any resistor. And if you take a look in your textbook, it will give you different symbols, for example, for switches, and where you would show that in your schematic diagram. So these two tables here nicely compare series and parallel circuits. A couple of things that I already mentioned. So this is as simple as we can possibly make it for the parallel and the series circuits. In this case, we have the resistors that are in parallel or in series rather than the batteries, and you need to show a minimum of 2. So for this first one on the left-hand side, so this is for the parallel, and we have 2 smaller loops, or we have branches. So that is the key. So as it says here, the circuit has the same potential difference across each branch. So whatever we have for the voltage coming out of here, if it's 1.5 volts, that's going to be the same that's going down this branch and that's going down this branch. Okay, so it is the same voltage on each one of the branches. The current that's going through each one of the branches, it could be different, so it doesn't need to be the same, and that would be determined by the resistors that you do have. Adding more resistors causes an equivalent drop in the total resistance. So we'll go back and we'll take a look at some calculations. So this one here tends to cause a little bit of confusion. So you add more resistors and the total resistance actually ends up dropping for this entire circuit. Add another branch with another resistor and the total resistance ends up going down. And the idea behind that is there are more routes for the electrons to take, and that's why the overall resistance ends up going down. Removing one of the resistors, what happens if we remove this resistor? The other one still works. The other one is fine. So how is that similar and how is it different with the series circuits? Well, we still have our same driving force here, which again we'll just say is 1.5 volts. So there's 1.5 volts that are going out of our battery that we have here. We have 2 different resistors, only now we don't have branches, it's one loop. It's one big loop that we do have. So whereas with the parallel circuit, we have the current that can take 2 different routes. In this case, it can only take the one route. So the current is now going to be the same through each of these resistors. For the parallel circuits, it could be different. For the series circuits, the current is going to be the same. Adding more resistors, in this case, adding more resistors causes the resistance to increase. So if I put another resistor in here, R3, the resistance overall is going to increase. If I add another resistor in here, it's going to decrease. So that's a big difference for you to understand between the parallel and the series circuits. And again, we'll take a look at that again shortly here when we do a calculation. Removing one of the resistors in this case causes a break in the circuit. You always need to have a loop to return those electrons back to the source. So if we remove this resistor, if we break this circuit or interrupt the circuit, then everything shuts down with a series circuit. I won't read through all of this at the bottom here, but it does say the series circuit. Again, here we have 3 of them, so a little bit nicer than at the top. So if we add another resistor to this one here, adding another resistor to this circuit again, and this is a big one, it will increase the overall resistance of this particular circuit. Adding another resistor here, that is going to decrease the resistance of this circuit. So let's take a look at another nice little animation here, really simple animation actually, that's showing this relationship between, or rather the differences between the series and the parallel circuits. I just need to go into Explore here rather than Chrome. There we go. Okay, so what are we taking a look at here? First of all, obviously right in the middle, what we do have is our battery, and it says that it's a 4.5 volt battery that we have here. Over at the right-hand side, we have some light bulbs that we can throw in. We have a whole bunch of different conductors, and it's going to allow us to connect these together. So this is really, really nice, this simple little animation, for a couple of reasons. We don't need to worry about any calculations. We're not talking about numbers. We're not doing this quantitatively. It's only qualitative. And this is as simple as you can possibly make it for the series and the parallel circuits. There are some limitations. Again, we don't have any numbers that we can take a look at. We can't make it quantitative. And we are also limited in terms of the number of lights and the number of branches that we can add into this. But it's still kind of nice in terms of introducing us to and visually seeing the differences between the series and the parallel circuits. So what I'm going to do is take in this platform here, which is going to allow me to insert a light into the middle. Of course, the light doesn't go on right now because it's not connected to the battery. So we need a conductor. So let's take this conductor here. Let's connect it to the battery. The electrons are coming out of this end of the battery. They're going into our platform here, which will have a conductor going through our L1, which is the light. The light doesn't go on because we need to complete the circuit. So in order to get the electrons moving, we also need to have this negative terminal connected to the positive terminal. So I'm going to drag this one in here, connect it to the battery, and as soon as we connect this one to our platform at the bottom, we complete the circuit, and the light is going to go on. So this one here, we have one single loop, so I suppose we could call it a series circuit at this point because it is one loop, but really, to truly call it a series circuit, we need to have more than one single electrical device. So let's drag in another electrical device, put them side by side here. Let's put our light in as well. Again, they're not going on because we haven't completed the circuit. If I plug this into the other side, we still haven't completed the circuit. We need to connect these two platforms together here. So I'm going to have a third conductor, which is going to connect our L1 to our L2. And then let's observe what goes on when we do make that connection. Okay, so now we completed the circuit and both lights go on. So pay careful attention to this. We don't have numbers here, so unfortunately, we can't measure resistance, we can't measure the current, so it is going to be all qualitative. So what I'm going to ask you to do is take a look at the brightness of the lights. So now I'm just going to eliminate this one here, by connecting this conductor to the top. Take a look at the brightness of the lights. So we have one single light. What happens if we connect two of them in series? We didn't change the voltage at all, right? It's exactly the same voltage that we do have. As you add more resistors, the overall resistance is going to go up. And we have the same current that's going through both of these. One single electrical device. As we add more and more devices in series, we're going to see the brightness of those getting lower and lower. So again, it would be nice if I could add in one or two more lights, but already we can kind of see the pattern, we can see the trend. So something else really significant, we only have one route for the electrons, right? They come out through the negative terminal of the battery, they pass through this light, they pass through the second light, and then they go back to the battery. So if I remove one of these lights, it interrupts the entire loop and electrons don't flow anymore. And this first fixture, it goes out as well. That light goes out. So you need to always complete the loop, and we only have one loop here. So let's change it up a little bit. So again, that one is for series. So now I'm just going to drag this one here down below, and I'm going to make it parallel. So now instead of one big loop, I'm going to have two smaller loops. So if I drag this wire over here, and if I put this blue one in here, so now I've created some smaller loops. So actually, let me just disconnect that one for a minute. So with this one connected, I only have this one light going on because it's not going through the second branch. Here we have two branches. I only have one loop. But as soon as I connect this other wire, now I have two loops. So now, take a look at the brightness again. So with the series circuit, I added another light in series and they got dimmer. Here, I add them in parallel. And notice that now there's no difference, or may even be getting brighter. So we have the same driving force coming out of the original battery, but we have electrons that can take two different branches. What happens if we remove one light now? The other one stays on. And that's because it's not one single loop, it's not one single conductor that we're interrupting. We still have the other loop or other branch that allows those electrons to flow. So very simple animation, but hopefully nicely shows for you the similarities and differences between these series and the parallel circuits. So let's just do a couple of calculations. Again, in your data booklet, you do have these equations in your data booklet. If I just go back up here to where that is in your data booklet. So now we're going to take a look at these two equations here. Resistance, if they're connected in series, total resistance if they're connected in parallel. So RT is for the total resistance, and all of the R1, R2, R3, and so on, those are for all of the different resistors that you have. So for series, we simply add them up. For parallel, it's 1 over the resistance, we add them all up. And then at the end, we need to take the reciprocal in order to get the overall answer. So reciprocal button on your calculator is this one here. Okay, so let's take a look at a couple of calculations with that. So the schematic diagram that we have here, you first of all need to recognize that this is a number of resistors that we have in series. What we have is one big loop here. So this is our battery that we do have. It doesn't tell us what the voltage is, but maybe this one here is we have a voltage that's equal to 9 volts, a 9-volt battery. Arrows show us the direction of the current going through our conductor. We have no branches here. We have one big loop, so the electrons need to go through each one of these different resistors. So let's just say that the resistance on this one is equal to 2 ohms. This one here is 5 ohms, and this one here is 10 ohms. So if I want to calculate the total resistance in this case here, well, this is our equation that we have. Let me just write it directly up here. So R1, what is it? 2 ohms. R2 plus R2 is our 5 ohms. And R3 is the 10 ohms. So the more resistors you have, we add together the resistance, and the total resistance is going to go up. Adding more resistance when we do have a series circuit causes the overall resistance to go up, and just simply adding all these together, we can see that the overall resistance is 17 ohms. So fairly simple calculation for the series. For parallel, it's a little bit more complicated. So we can see here, obviously, that we have different branches, and that tells us that it is a parallel circuit. Let's just use exactly the same numbers. So 2 ohms, the resistance for R1, 5 ohms, the resistance for R2, and 10 ohms, the resistance for R3. So now 1 over the total resistance, not the total resistance, but 1 over the total resistance, is 1 over 2 ohms plus 1 over 5 ohms plus the 1 over 10 ohms. So plugging this into your calculator, I like to do it this way. I just like to open up some brackets, go 1 divided by 2, close the brackets, plus 1 divided by 5. Again, you always need to close the brackets, add the last one in here, 1 divided by 10, close the brackets, and then press enter. And then what it's going to give you for an answer here is 0.8, but that is 1 over the total resistance. So if we want the total resistance, we need to take the reciprocal of this. So 1 divided by this, or if you just simply use this one here that I showed you before, this is the reciprocal button, x to the negative 1, and that then gives us RT, the total resistance, which is equal to 1.25 ohms. So as we add more resistors, the total resistance goes down. So if we were to add another one here and put this in as 20 ohms, this number would get even lower. And that's because the electrons have more routes to take because there are more branches. If we go back up to this one here, if we were to add another one in here and call this one R4 and make this one 20, well, then we would just add it to this one here, and it would end up being now 37 ohms for the resistance. In series, the more resistors increases the total resistance. In parallel, the more resistors is going to lower the total resistance.